All right. So what I'd like you guys to do. First thing I want you to do is I want you to have your complete your figure. Once your figure is complete, I want you to take your paper and I want you to fold it like this. So it's like they call it the hot dog fold. But I want to make sure that your drawing is on the outside of the hot dog fold. Okay? Fold it so you're drawing. And guys, and you want the seam to be right down your line. Okay? You want the seam to be right down your line. You want the fold to be exactly on your line. Okay? If that means you fold it first and then draw your lines, that's fine too.
Should have shown this.
I don't know. But now you're learning a new skill of folding right down the line.
No, because it's not even.
Okay. Then, once you've folded yours, okay guys, once you fold yours over, hold your paper up so that you can see your figure through the paper. Okay? So the side that you didn't draw on, you drew one in every quadrant. You just need one quadrant. Okay. So maybe you do want to start over.
Can I start over?
Yeah, you can start over if you want to. Alright. Pull a hot dog and hamburger and draw.
Okay.
Yeah.
You want pencil?
Okay. So, Maddie, you'll pick that up later.
Yeah, you picked that up later.
Okay. So, fold it so that you have a little hamburger fold, and then you can see through your fold. Okay, so have your figure on top, your figure's facing the lights, and you're looking up so you can see at least the vertices of your figure. You need to redraw a little darker. Okay? Then, put a dot at each of the vertices. Okay, put a dot at each of the vertices. Well, looking up. The vertices are where they connect, so like, put a dot at A, B, and C. So put a dot at each of the vertices. Wish I had the camera turned on you guys right now. Oh, good thing I let you fill that up. Okay. So, you put a dot at each of the vertices, then bring your paper back down, use your ruler, and connect the vertices. You might need to hold up so the light gets. Okay, so here's your first one, right? So A, B, C. Put dots right there. Okay, and then bring it back down and redraw. Oh, no, hold it up and put the dots. Like this. Maybe that. Now connect them.
What are we supposed to do now? Mark it where the A and B is.
Yep, and then bring it back down and then connect your dots. Okay. Yep. So then if you open it up, you have two of your figure. Okay, does that make sense?
Yeah, let me get you one.
Okay. So, if I were to do that with my paper right here, okay, I were to fold it, and then I were to open it back up after connecting my dots. How would this look? Would it be like this?
No.
Would it look just like that?
No.
No, what would it look like?
It will mirror like
It would look like it's looking in a mirror?
Yeah.
Okay, so it'd be like this. Kind of like
It
that?
looks the same. No. Yeah.
Why not?
Well, you tried. Yeah.
I tried. Okay. It should be what?
A reflection.
Okay, it should be like identical, right? Is that better?
Yeah.
Okay. It's close, right? Well, the figure should be exactly the same, just, you guys said mirrored, right?
Mm-hmm.
Okay, so it's like you're looking in a mirror. So the green one is like the reflection of the blue one. So the blue one is like me looking in the mirror. The green one is what I see. Right? Does that make sense? Okay, let's try the other way now. Take your paper, go back to rectangular. All right, now give me a hamburger fold down the x-axis. Okay, I don't know why it's a hamburger. It doesn't turn into a circle.
That's what I said.
Never made sense to me. Okay. My first grade teacher loved it though. Hamburger, hot dog. I always fold the wrong way.
So, no, I never realized until you said that.
Yeah.
That they call it hamburger and it's not a circle.
They should call it sub sandwich.
But it's a bun.
It's a Subway fold.
Not fake.
Right? Then hold your paper up so you can see your original image again. Just your original. You can do both if you want to, but you only need to do your original one. Your original one should be on the right side. Okay? Hold it up and put the dots.
That was funny.
It's alright, I'll watch it later and see what he said.
He didn't say anything.
He didn't say anything?
No, this is funny.
I can't tell which one's your original.
But you do it on both?
Here.
But you do it on both squares?
Nope, just one. You can do both if you want to. Perfect. Okay, so how does this one compare? So what would happen here? Would it just be like this? Would it be like that? No. What changed here? It's really like this, right? Yeah. And how do those figures compare?
Reflected.
They're identical, but they are flipped, right? It's kind of like that whole mirrored thing again, isn't it? Okay. So since these figures, when we folded and retraced, they look identical, like we're looking in a mirror. This isometric transformation is called a reflection. Now I use two big words there, isometric and transformation. Okay? Because we are learning about things called isometries. Okay? An isometry is also known as a congruence transformation. Why do you think it's called a congruence transformation? Let me write this a little better. Why do you think it's called a congruence transformation? How does the image compare to the original?
The distances are the same.
How does the image compare to the original?
It reflects it.
They're congruent.
They're congruent, right? Okay. Now, before I give you a definition of reflection, I want to talk about the images that you made. Okay. Your first thing that you drew is called the pre-image. Okay. So the one in the top right corner, that's called the pre-image. Okay. The pre-image is your original figure. Okay. Interesting. The pre-image, guys, is your original figure. It'll be labeled with just like A, B, C. Okay? Your image is what?
Reflection.
Okay? It's what we get after we reflect, right? Your image is the result. So it's like when you look in the mirror. Which one's the real image? You're the real thing, right?
Yep.
Right? The thing across from you, that's the image of you, right? So you're the pre-image, you're the real thing. That thing across from you is the image. Okay? So the image is the result of the transformation. Okay? And we denote the images by using things called primes. Primes are just apostrophes. So if we go back to our drawing from earlier, okay, back to our drawing from earlier, this blue one right here, Maddie, this blue one is my image or pre-image? Pre-image, this is where I started, right? The green one is a image. So I denote images by putting apostrophes. Okay, so you can do that in yours. Okay? This black one, image or pre-image? Image. Because it's the blue one reflected over a line. Does that make sense? Does that make sense? Okay. So definition of reflection. Let's see what it is. Okay. A reflection, guys. Oh, didn't for isometry. Get ahead of myself. An isometry or congruence transformation. An isometry or congruence transformation is a transformation that produces an image that is congruent to the pre-image. Okay? So this is a transformation that produces an image that is congruent to its pre-image. And we remember that the image is the original, or sorry, the pre-image is the original, the image is the result. Now, two figures are congruent. That means that their side lengths and angle measures are all the same. So corresponding sides and corresponding angles are all equal. Josh, stop down this one scale. I can't give you anything. Why? Because it's medicine. It's candy, basically. Can't give you any medicine. All right. A reflection. What do you guys think a reflection is? Okay.
What?
So a reflection is it? Do you think it's a congruence transformation?
Identical.
Is our pre-images and images identical? Yeah, they're exactly the same. Their orientations change. They might have flipped, right? But everything's exactly the same. Angles and side lengths are the same. So a reflection is a congruence transformation. It makes the exact same figure. It just flipped or rotated, or not rotated, it just flipped over, facing a different way. So a reflection is a transformation where a pre-image is our original, right? Is reflected across a line of reflection. You know what I'm saying? Mr. Branch, you can't use the definition, you can't use the word in the definition. I did. I used reflected and line of reflection. This is a noun right here. Okay. So I didn't use the word in the definition.
Ew.
Okay. All right. I'm missing my. All right. Does that make sense? Does that make sense, guys? Okay. So what does this mean? So let's say here's my paper. Okay, you guys all have your papers over there? Yes. And let's say this time I'll draw a different figure. So much different.
Oh, yeah, that's...
Completely different. A, B, C. Okay. Now, if I fold this along the y-axis, so right here, right? What's it going to look like over here? You have any?
Question over there.
Which question, Rebecca?
What's the little like dashes? Like if you go over, I can't say it because you're staying in the way. But underneath it says underneath the word result. What's the little dash thing?
Those are apostrophes. They're called prime. It means that is the image. So no primes means pre-image. Primes mean image. Okay. So how's this one going to look?
ACB.
Where's the point going to be? Is it going to be close to the y-axis or far away from the y-axis?
However far it is from the other side.
Yes, I tried. Should be identical, right? But it'll look like that, won't it? Right? Where this is my pre-image and this is my image. We know because of the primes, right? Does that make sense, guys? Okay. Now, the y-axis, this axis right here, that's what I reflected across, right?
Yeah.
So this is my...
Line of reflection.
Good. It's my line of reflection.
Is it always going to be either X or Y?
It will not always be either the x or y axis. We're going to start with just those. Okay. But there's a simple thing you can do to figure out where it will be if it's not the x or y axis. Okay. Now, you guys have made some images and pre-images, right? I want you to take your pre-image, pick a point on your pre-image, and measure to the line of reflection, and then to the point of the image. So I mean, I want you to take your ruler, okay, and I want you to measure how far A is from the line of reflection, and then how far A prime is from the line of reflection.
In centimeters.
Centimeters, meters, inches, I don't care. Pick something, okay? Fingernails, whatever you want, okay? Fingernails is a little inaccurate, though.
Do we start from 0 and start at 1?
0.
What? Like,
I don't quite know what this is. Oh, you said start at 0, not the
Yep, just like put the 0 on the line of reflection and see how far A is away. Then put the 0 on the line of the reflection and see how far A prime is away.
This random.
I don't know what this is.
I don't know how to read rulers.
You know how to read rulers?
Me neither. Like, I know how 1, 2, 1/2, but little dashes after half. How do I say that?
Okay, so that's like 1.7.
Oh my god.
Okay. You just count the number of dashes.
Oh, okay.
If you're using millimeters.
Oh, you said
So that's like 1 point. That's like 1 and 15/16. Or if you do this way, with the millimeters, the number of dashes is point whatever. Hey, look, it's 5. We'll go fast. Millimeters is 5. Millimeters might be easier because it's not fraction denominated. They're units of 10. It's not like 1/4, 1/2, 1/8, and so on. Inches are 1/4, 1/2, 1/8. But we have an idea, guys. What have you noticed? They're the same? So if A to the line of reflection is 3, how far is A prime away? 3. If B to the line of reflection is 6, how far is B prime? 6. If C is 4 from the line of reflection, how far is C prime? 4. So the pre-image and image are equal distance from what?
The line of reflection.
Perfect. The pre-image and image are equal distance. Are equal distance from the line of reflection. Does that make sense, guys? Does that only work with the y-axis? Would it work with the x-axis too? Yeah. Does that make sense? Yeah, does that make sense?
Yeah.
Yeah. Now, what's the relationship between A, B, C and A prime, B prime, C prime?
Same.
They're the same, meaning they are congruent. Are there any questions about what a reflection is and the equal distance part? Any questions? Okay. Now, Faith, you brought up a good question. You said, are we always going to use the x and y axis? Right? So, if I'm using the x and y axis, I can figure out where the points are based on how far they are from that axis, right?
Yeah.
Right? What if I used a line that wasn't on the x or y axis? Let's say I reflected across that line. It's not the x-axis, right? Right? If I want to find where C was located, how can I do that?
You just count the distance away from the line that you want to do.
Perfect.
You don't have to put that in
So,
words, but,
if this y value, let's say this is like 2, 4. Actually, it'd be 4, 4 from over next. Okay, if that's 4, 4, right? Let's say this line is at 3. How far is C away from that line? It's 1 unit, right? So where will C's image be? It'll be 1 unit below the line, right? Which will be 4, 2. Does that make sense? So if the line is not the x-axis or y-axis, you just count how far you are from that line, and then put your point on the other side that same distance. Does that make sense? Any questions? No? Okay. That's all I have for today.